So you might be asking the question, why are we devoting an entire learning unit to photosynthesis? Isn't this biochemistry and we're learning about disease and everything? Yes, but two reasons. First, we're going to be able to review and understand a lot better what happens with mitochondria when we look at the parallels with what happens in chloroplasts. And then secondly, when we really learn about that, we realize plants are pretty cool with some of the cool biochemistry that they can do. So that being said, a lot of the videos that we're going to have in this learning unit are going to be sort of a compare and contrast with what we know with mitochondrial electron transport in biochemistry, and then chloroplast electron transport in biochemistry. Remembering that both of these organelles, the theory is that they used to be prokaryotic bacteria that had magic properties like the ability to use chemical compounds and make energy like ATP, or to use the sun and make chemical compounds like ATP. And then they got swallowed up by another organism who said, hey, I'll give you a home. That's going to be pretty cool. We can have this symbiotic relationship. And so that was sort of the origin of modern day mitochondria and chloroplasts. Both were ancient bacteria. So a lot of compare and contrast we'll do here. So the first compare and contrast is just thinking about the different equations for biochemistry that happens within both mitochondria with fuel oxidation and then chloroplasts with food production. So going a little bit more quickly on the left-hand side, since this is something we've done already, so we're going to have fuel oxidation. So fuel plus oxygen is going to give us our carbon dioxide, water, and then energy as ATP. So sort of connecting pieces here together. Our fuel is oxidized. And when our fuel is oxidized, oxidation again is the loss of electrons. So we're going to lose electrons. Those electrons are going to go to our middlemen, our B vitamins, NAD plus and FAD. Those are reduced to make NADH and FADH2. So that's again how we harvest and hold on to those electrons from our fuel metabolism, is we harvest them as those middlemen. As those become oxidized, they are going to deliver their electrons to the electron transport chain. Okay? The electron transport chain allows the movement of electrons through a variety of carriers that are going to allow us to generate a proton gradient. And then through that process of oxidative phosphorylation, we're going to generate ATP. Well, as those electrons finish going through the electron transport chain, they are going to be delivered to molecular oxygen, and molecular oxygen is reduced to make water. So the last piece to fill out here is, well, how again do we make our carbon dioxide? Well, remember, there's several processes, metabolic pathways that we learned about that generate CO2. The two main ones that we utilize for the combustion of carbohydrate-derived fuels are pyruvate dehydrogenase chemistry, and then all fuels can utilize the citric acid cycle. So that was a lot there, but hopefully that's a review because we've already gone through the details of all of these processes of fuel oxidation. So one of the pieces that I want to make sure to highlight here, and again, draw a parallel and a contrast with what we know with fuel production when we think about what happens with chloroplasts, is these molecules, right? This is where we get our electrons to go to the electron transport chain. These are high energy by virtue of their chemical composition. So these are high energy by virtue of their chemical composition. And we'll see why this is important and relevant when we learn a little bit more about electron transport in chloroplasts. But basically, NADH and FADH2 holding onto those electrons are high energy molecules. And in doing so, they are able to go through the electron transport chain and use that energy to pump that proton gradient. All right, little experiment here that I want to highlight before we kind of go through. Pause here for a second. little experiment. And in today's age, this would be like a little science fair experiment, right? But it was groundbreaking sort of at the time. I'm going to draw a little beaker here. I'm going to draw a candle in here. Let me zoom in so we can sort of see what's going on here. I'm going to draw a candle here. Okay, we've got a flame on our candle. Okay, now what Joseph Priestley noticed is when he put a candle inside of a beaker that was overturned and he lit that candle would burn for a little while, and then after a while, the candle would go out. We now know and understand that what's happening is that fuel combustion is going to utilize oxygen, generating CO2, and once that CO2, or once all of that oxygen has been used up, fuel combustion must cease. So the candle would go out. Second part of the experiment, okay, is we're going to take and we're going to keep that same extinguished candle that's sort of in this beaker that's overturned, and we're going to let it sit in there with a plant. Okay, so I'm going to have, let me draw a better little plant there. Okay, we got a little plant that's there. Okay, wait a little while, and then go back in and you will be able to relight the candle. Now, obviously we have to make sure we don't let any, oxygen in from the external environment. So lots of controls there. But notice that the candle was able to be relit, which must mean putting that plant in there reintroduced oxygen into this environment. And therein was the start of our understanding with what happens with fuel production. Now, one of the things that's pretty cool with two things that we're going to see in this learning unit, this slide dealing with fuel oxidation and fuel production, and then once we start talking about the Calvin cycle and looking at it in relationship to the pentose phosphate pathway, we'll see that there's sort of, a yin and a yang, if you will, opposite sort of situations here. We're going to go through a little bit more slowly with this equation because it's the first time that we're sort of seeing it, but it's going to be an opportunity to see the parallels with what we have with fuel oxidation, and then in a 30,000 foot view way, sort of understand how the process of photosynthesis works. So let's write down this equation for what's happening here. We're going to be taking water, carbon dioxide, and energy, and we're going to be making carbohydrates and then molecular oxygen. So going a little bit more slowly through all of these steps so we can see how this happens. Well, where we get those electrons is we get them from the splitting of water. Okay, so the oxidation of water is going to generate electrons. These electrons are going to go through an electron transport chain. Okay, going through the electron transport chain generates a proton gradient. Okay, that proton gradient is used to synthesize ATP. Okay, so one thing I want to highlight here, you'll note here I added that this is mitochondrial electron transport over here. I'm going to use blue anytime I'm talking about mitochondrial electron transport or anything with mitochondria. We're going to be talking about chloroplast electron transport over here. So when we talk about the use of this proton gradient to synthesize ATP, we call it oxidative phosphorylation in mitochondria. We're going to call it photophosphorylation when we have it in chloroplast. So again, a compare and contrast here. This up here is photophosphorylation. Okay, so let's talk about now sort of what happens and where those electrons get delivered, right? In mitochondrial electron transport, they were delivered to oxygen to make water. Now they're going to be delivered to NADP+ to make NADPH. So again, this is the reduction process and we make NADPH. Okay, so a few other things to highlight here, that NADPH is important because this is going to be used for reductive biosynthesis. Okay, remember where we've seen NADPH before. We've seen it in the pentose phosphate pathway. And that was important because that was a way to generate a place where we had electrons that we could use as glue to hook atoms together to make bigger molecules. The same is going to be true here. So we're going to talk about that in just a second. Okay, let's fill in a couple of other pieces here. Remember, when water is oxidized, loses its electrons, we generate molecular oxygen. So this again is an oxidation process. Okay. One other thing to sort of highlight here and think about with these electrons, in order to go through the electron transport chain, they have to be high energy so that they can flow downhill. When we talked about those electrons in mitochondrial electron transport, as I should point here to NADH and FADH2, they were high energy by virtue of their chemical composition. So let's actually fix this arrow here. It's really these guys that are high energy by virtue of their chemical composition. Okay? So the question is how do we get high energy electrons then for chloroplast electron transport? Because water is not a high energy molecule. Well, this is where the magic comes in with what chloroplasts are able to do, that these electrons become high energy by the sun. We're going to see how that happens in a little bit. The sun is going to use wavelengths of light to excite those electrons to high energy states. Okay, so that's how that process is going to happen. Okay, so what we've actually shown here with doing the synthesis of NADPH and the production of ATP using a proton gradient is what we refer to as the light reactions. So these light reactions ultimately generate ATP, NADPH, and then oxygen. So those main energy molecules, ATP and NADPH, are made in the light reactions. Okay, now we're going to talk about what happens and even though historically these have been called the dark reactions, I'm going to try to not use that formalism at all because I think it can be confusing because it makes it seem like they happen at nighttime. And they don't. So I'm going to call these next set of chemistries that happen the light independent reactions. Okay, so we've got the light reactions, and then we're going to have the light independent reactions. Okay, and ultimately this is where we're going to use the energy from ATP, the electrons from NADPH, and we're going to glue carbon dioxide molecules together, that's called carbon fixation, and generate carbohydrates. Now, when we'll learn the details of this, we're not plucking individual carbon dioxide molecules and putting them together, but the net is taking carbon dioxide out of the atmosphere, hooking it to molecules that become carbohydrates. Okay, so the light independent reactions are going to use ATP and NADPH to make carbohydrates. Okay, so as we're going to see here in a second, this ATP is going to provide the money, the NADPH is going to provide the electrons, and we're going to, the net, glue carbon dioxide molecules together to make carbohydrates. Okay, so with some arrows, let's sort of draw how this happens here. Okay, so NADPH is going to be providing electrons. They're going to take carbon dioxide molecules and reduce them. So this is again reduction, running out of room here. So we're going to have reduction there. Okay, that's also called carbon fixation. And this process can't occur without the input of energy, biological money, so that ATP is sort of used for that process. Okay, so highlighting here one really important piece, these light reactions, these light independent reactions, historically called the dark reactions, these only occur when the sun is out. Okay, and we'll talk about in another video how we control for that piece.